First, I thank to all organizers for inviting me. I'm very great honor to be giving lectures based on my research. Really appreciate it. So through these lectures, we study the topics, distance regular graphs, and double affine algebras. Roughly speaking, we will discuss the relationship between Q-polynomial distance regular graph and double affine algebra, which relationship is described as like, for each delta clique of graph gamma, indices is an irreducible module for a DAHA of rank 1. To find this link, we're going to use a semi-simple matrix C algebra. I will use the bold T because that is the somehow generalized Théorie algebra. And also, we will use the theory of Leonard system. So for more detailed information, please refer to the paper, Q-polynomial distance regular graphs and double affine algebra of rank 1. So let me first begin with some preliminaries concerning Leonard system. So we use the following notations. We use D, a positive integer, and met D plus 1 C means the C algebra consisting of all D plus 1 by D plus 1 matrices that have entries in C, and let V denote a vector space over C with the dimension D plus 1. And V is the C algebra consisting of all linear maps from V to V. And for an element A, we say A is multiplicity free whenever A has D plus 1 mutually distinct eigenvalues. So let's say A is multiplicity free in and V, and let theta I be an ordering of the eigenvalues of A. Now we denote Vi, the eigenspace of A corresponding to theta I. We define a linear map, EI, satisfying these equations you see there. So EI minus I Vi is 0, and EI Vj is 0 for J differs I. In other words, EI is the projection onto the space Vi. We easily see that EI Ej is delta Ij Ei, and sum of all EI is identity element, and A is the linear combination of EI with eigenvalue theta I. Call this EI primitive identitant of A corresponding to theta I. Théorie introduced the notion of a Leonard system. This is kind of linear algebraic version of Leonard theory. So by Leonard system on V, we mean just a sequence of elements in and V, A, EI, and A star, EI star. And these elements satisfy these 5 conditions. So each of A star is multiplicity free, and EI 0 to V is an ordering of primitive identitants of A, and EI star is kind of a dual version of the second condition, and condition 4 and 5. So in previous lecture, Professor Théorie introduced the concept of a tridiagonal system. So this is the special case of the tridiagonal system. So each eigenspace has dimension 1. We refer to D as the diameter of phi, and we say phi is over. And when we have Leonard system phi, then we have 3 more Leonard systems, namely phi star, phi down arrow, and phi double down arrow. So phi star is just we just switch A and A star, the dual version, and down arrow, single down arrow is everything is fixed, but we take the reverse ordering of a dual primitive identitant EI star, and double down arrow, we fix all elements except the primitive identitant of A. We just take the reverse ordering of EI. Now, let theta I be the eigenvalues of A associated with EI. And we called the sequence of eigenvalues the eigenvalue sequence of phi. and theta I star dual eigenvalue sequence of phi. And it's known that there exist non-zero scalars, say var phi I from 1 to d, and C algebra isomorphism from n to b to met d plus 1c, so that the image of A is lower bidiagonal matrix, and image of A star is upper bidiagonal entries. Each entry is, eigenvalue sequence and dual eigenvalue sequence together with the sequence of var phi I. So we name this, we call this the first split sequence of phi. And we apply this argument to double down arrow. So the first split sequence of phi double down arrow is called the second split sequence of phi, original Leonard system. Okay, so we have 4 sequences of scalars, and Terwilliger also introduced the concept of a parameter array over C of diagonal D. That is just a sequence of scalars, theta I, theta star, var phi I, satisfying these 5 conditions. So first condition means our scalar theta I and theta star mutually distinct, and var phi and phi non-zero scalars, and var phi condition 3 satisfies this quantity, and condition 4 also, phi satisfy this quantity, and last condition, these 2 quotient expressions, theta I minus 2 minus theta I plus 1 over theta I minus 1 minus theta I, and each dual version, they actually equal to each other, and this quantity is independent of I. When this scalar, the sequence of scalar satisfy this 5 condition, we call this sequence parameter array over C. Using this parameter array concept, Terwilliger classified all Leonard systems. So here is the theorem. So suppose we have a sequence of scalars from C. The first condition and second condition are equivalent. So if the sequence is parameter array over C, then there exists a Leonard system that has eigenvalue sequence theta I, dual eigenvalue sequence theta I star, first split sequence of var phi I, and second split sequence phi, and vice versa. So by this theorem, we find a one-to-one correspondence between the set of isomorphism classes of Leonard systems over C and parameter arrays over C. When we have a Leonard system phi, we say, this parameter array over phi means this sequence is actually parameter array over C corresponding to the Leonard system phi. Okay. Now we discuss further about the Leonard system. So here is our Leonard system phi, and we choose a non-zero vector, say V naught, from E naught V, and we think of the sequence of vectors EI star V naught, where I is 0 to D. Then it turns out that this sequence is a basis for V, and we call this phi standard. Phi standard basis is nice because with respect to this basis, the matrix representation of A and A star are given as you see here. So A is tri-diagonal tri-diagonal matrix, and A star is diagonal matrix. Actually, the tri-diagonal matrix is the irreducible. In other words, BI, CI non-zero scalars. We call this entry AI, BI, CI the intersection numbers of phi. And this matrix A, matrix representation of A, satisfies the constant raw sum with. And when we have this Leonard system, together with intersection numbers, we can express all intersection numbers as the parameter array. So BI, CI, and AI are parameterized as parameter arrays, as you see here. Now, with respect to our Leonard system, we define a polynomial UI by you see here. So ui is the sum of this quantity. Then this polynomial ui satisfies these three-term recurrence relations. When we evaluate this polynomial ui at theta j, where theta j is the eigenvalue sequence of Lorentz system, then it satisfies these three-term recurrence relations where Ci, Ai, Bi are intersection numbers of Lorentz system phi. So as you see here, we obtain the polynomial ui from Lorentz system phi. Similarly, we can also obtain the polynomial ui star, let's say ui star, from the dual version of Lorentz system phi star. Then two sequences of polynomials, ui and ui star, satisfies these nice relations called Askey-Wilson duality. 1990, I think maybe 1980, early 1980, the Leonard proved that the polynomial satisfying this Askey-Wilson duality is actually the Q-Racah polynomials and its limiting and special cases in the Askey scheme. Actually, there is a relationship between these polynomials and parameter arrays of Lorentz system phi. Let me briefly explain how. When we have, Lorentz systems, we obtain the corresponding parameter arrays. With that parameter array, we construct this polynomial ui, and we evaluate this polynomial ui at theta j. We classified all parameter arrays over C. Then those parameter arrays fall into exactly 13 families. So for each family, we evaluate the polynomial ui at theta j. Then that becomes this polynomial forms one of these polynomials in the Askey scheme. So we call this family the class of orthogonal polynomial terminating branch of Askey scheme. For more detailed information about this theory, please refer to these two papers. Especially second paper is about the more orthogonal polynomial area. So actually, I listed all 13 families named Q-Racah, Q-Hahn, dual Q-Hahn, and so on. But among them, the Q-Racah type is the most general case, and remaining 12 is actually the limiting and special cases. So let me just give an example for Q-Racah type. So we define the scalars, sequence of scalar, theta I, theta star, phi I, and phi I, as you see here. Those scalars are parameterized in terms of H, H star, S, S star, R1, R2, and Q. And these parameters satisfies these conditions. R1, R2 is S, S star, Q to the D plus 1. Also, to avoid the degenerate situation, we just assume these conditions. Then it turns out that this parameters satisfies all these 5 conditions. So no, it's okay. Actually, I tried to click this button with the mouse, but anyway, if I click this, then we back to the parameter array definition, 5 conditions. Those 5 conditions satisfies. And with this expression, we choose ij, and we evaluate ui lambda with the. It turns out that ui of theta j is the expression of the sum end of, you see there, the line 1, and where aq sub n is actually the product of n factors. And by definition of basic hypergeometric series, this sum 1 is actually the Q-Racah polynomials. So that's why this is to explain how our parameter arrays, actually more essentially, Lorentz systems is related to the orthogonal polynomials in the terminating branch of Askey. Okay, so that's all the contents we need in this lecture. And now I'm going to move the preliminaries for distance regular graphs. Thanks to Professors Cullen and Terwilliger, they already, give many basic definitions on the distance regular graphs. So I may just go quickly for these basic notations and terminologies. And now for this session, we use the following notations. So our X is non-empty finite set, and R is just a set of two elements subset. We call this H. And gamma is a graph, actually connected a simple graph with a vertex set X and edge set R. And we use the notation partial notation, that is just a shortest path length distance function for gamma. And we also define the diameter of gamma. And we use the notation gamma IX, that is nothing but the ith subconstituent of X. Distance regular graph, I think this is a third time to introduce today. So anyway, gamma is distance regular whenever for all integers hij between 0 to d and all vertices x and y with their distance is h. The cardinality of the set intersection of gamma ix, ith the subconstituent of x, and j's subconstituent of y depends only the integers hij, not on the choice of vertices xy. We denote this cardinality by phij and call this intersection number. So examples: Hamming graphs, Johnson graph, Grassmann graphs. So the intersection number phij satisfies this clique property. Actually, this is the triangle inequality, but I just call this the P polynomial property. So phij is 0 if one over hij is greater than the sum of the other two, and non-zero if one over hij is exactly equal to the sum of the other two. So in what follows, we assume our graph gamma is distance regular with diameter d greater than or equal to 3. And we abbreviate the intersection numbers, Ci, Ai, Bi. You see there, so the picture really helpful to understand the this abbreviation notation. Now we use this notation. So mat xc, the C algebra consisting of the matrices, rows, columns are indexed by x, and we define the matrix A in mat xc. Xy entry is 1 if their distance is I and 0 otherwise. And we call this matrix the ith distance matrix of gamma. In particular, I equals 1, we call this matrix adjacency matrix and abbreviate just A. Combinatorial regularity leads to algebraic relation. The product of two distance matrices AI, AJ gives a linear combination of distance matrices AH with coefficient intersection numbers PHIJ. And we easily see that, AI, AJ commit to each other. Also, by setting J equals 1, then we have this product AI, AJ is just a three-term recurrence. PI minus 1, I1 is just a BI minus 1. And middle term is, the coefficient is AI, and the third term just the CI plus 1 by using the abbreviation notation. And also, there exists a polynomial Fi satisfying degree F is I, and AI is exactly the image of Fi of A. So actually, in previous lecture, Théorie introduced this polynomial as the VI, but I just used the Fi. And let's think about the subspace spanned by all these distance matrices. Then by these algebraic relations, we have the algebra, and we call this Bose-Messner algebra. And this algebra satisfies these properties. So obviously, M has basis AI because they are linearly independent. And this is generated by the adjacency matrix A. M also has the second basis EI, satisfying these properties. Also, there exist real scalars theta I satisfying this. And we call this coefficient theta I the eigenvalue of gamma associated with the EI. Now let me leave this circle, and let circle denote the entry-wise product in the matrix algebra mat XC. Then clearly, AI circle AJ is delta IJ AI, so N is closed under the circle, and because EI is a second basis for M, the product of EI EJ is a linear combination of the second basis with the coefficient QHIJ. Actually, these scalars QHIJ are real and non-negative. So this is nice positivity in algebraic combinatorics. We call this claim parameters of gamma. And likewise, the intersection number AI, BI, CI, we abbreviate AI star, BI star, CI star. So now I define the now introduce the P polynomial property. So our distance regular graph gamma is said to be a Q polynomial with respect to the ordering E0, E1 through ED. Whenever our claim parameters satisfy this triangle inequalities. Actually, this concept is the dual version of the P polynomial property. In fact, this definition is very formal definition. So if you want to really understand and learn to the more practical method, please pay attention to the Professor Tolliger's lecture. If gamma is Q polynomial, then we have this equation, EI circle E1 is a three-term recurrence. And likewise, in a P polynomial property, we have the polynomial Fi star such that the degree of Fi star is I and EI is Fi star of E1, where this polynomial multiplication is obviously entry-wise product. So now for the rest of this lecture, we just assume that our graph gamma is Q polynomial with respect to the fixed ordering E1, E0, E1 through ED. All right, now we fix a vertex X and we define the diagonal matrix in this matrix algebra with YY entry is 1 if the distance between XY is I and 0 otherwise. And we call this diagonal matrix I is the dual primitive identitant of gamma with respect to X. One can find that this EI star EJ star is delta IJ EI star, and the sum of EI star is identity matrix. So using this, we think of the subspace spanned by this dual primitive identitant. M star is the subalgebra of math. We call this dual Bose-Meissner algebra with respect to our fixed vertex X. Because we define the dual primitive identitant, so it's natural to define the dual adjacency matrix. So we recall the primitive identitant EI. We define the diagonal matrix AI star of X, satisfying the YY entry, diagonal entry of AI star is the XY entry of EI times the size of X. And we call this AI star, the dual distance matrix of gamma with respect. It turns out the sequence of these dual distance matrices form a basis for a dual Bose-Meissner algebra. And their product is the sum of AH star with coefficient QHIJ. So this is exactly the dual version of the distance matrix multiplication. So it's very natural to say this is dual distance matrix. Now, when I is 1, we say A star, dual adjacency matrix of gamma with respect to X. And in fact, our dual Bose-Meissner algebra is generated by A star. Because we have two bases, let's express A star as the linear combination of EI star with the coefficient, and we call this theta I star, the dual eigenvalue of gamma associated with EI star. So, so far we discussed the Bose-Meissner algebra and dual Bose-Meissner algebra M star. And we define bigger algebra. So let T Tx, actual Tx, denote the subalgebra generated by M and M star. Then this algebra is called the topological algebra of gamma with respect to base vertex x. Then by our discussion so far, this topological algebra is generated by addition symmetrics and dual addition symmetrics A star. And this is finite dimensional and non-commutative in general. And this is semi-simple because this is closed under conjugate transpose map. This algebra, we have relations. So triple product EI star A EJ star is 0 if the difference between IJ is greater than 1. And the second relation, the dual version of the first relations. So we discussed this topological algebra, and we recall the notion of a T module. We just index our vector space V, our finite set X, and we view this vector space as left module for the matrix algebra XC. Then by T module, we mean a subspace W such that VW is contained in W for every element. And we called T module W is irreducible whenever W is non-zero and W contains no T modules other than 0 and W. So let's say W denotes a T module. As we discussed in the previous lecture, W decomposes into an orthogonal direct sum of irreducible T modules. In particular, the left module V is an orthogonal direct sum of irreducible T modules. Sometimes we call this standard module. I introduced some terminologies concerning T module concept because it's very nice to describe the T module structures. Let's say W is irreducible T module. Then this T module is direct sum of the non-zero spaces among this EI star W, and also direct sum of the non-zero spaces among EI W. Of course, it could happen, for some J, EJ star W could be 0, could be possible. So we define the by the endpoint of W, we mean the minimum index I, such that EI star W is non-zero, and dual endpoint is just the dual concept of the endpoint. And the diameter, we just count all the subspaces EI star W, which is non-zero. And dual diameter is this. In fact, diameter of the irreducible T module is equal to the dual diameter of the irreducible T module. Another important concept is thinness. So if the dimension of each subconstituent space EI star W has dimension less than or equal to 1, then if and only if dimension of EI W is less than 1. So if all subconstituent spaces has dimension at most 1, then we say this module structure is thin. So I'm going to give an example of thin irreducible T module. So we denote x hat, the vector in V, with the entry 1 in x coordinate and 0 or others elsewhere. And we call this characteristic vector of x. Now let's think about the space mx hat. Then easily see that this space mx hat has basis ai x hat and also ei x hat.
A single vertex. Sorry.
Yeah, and we denote the bold one, all ones vector. This vector satisfies these equations. So ai x hat is ei star all one vector, and the dual version ai star all one vector is ei x hat times the size of x. So from these equations, we can say the mx hat is actually equal to m star all one vector. These two subspaces equal to each other. Therefore, mx hat is T modules because mx hat is invariant under every element in T because T is generated by m and m star. And this space mx is actually thin, irreducible T module, and endpoint 0, dual endpoint 0, and diameter d. So in other words, all subspace EI star, mx hat, and EI mx hat, non-zero one-dimensional space. And we call mx hat the primary T module. Okay, this is the example of the thin irreducible T module. This is the lemma. When we have the thin irreducible T module with endpoint sigma, dual endpoint sigma star, and diameter rho, then the sequence of elements you see there, these elements act on thin irreducible T module as a Leonard system. So, when we recall the primary T module mx hat with endpoint 0, dual endpoint 0, and diameter d, then this element acts on mx hat as a Leonard system, and this is called the primary Leonard system. And also the corresponding parameter is called the primary parameter array. And because we have a Leonard system, what is the standard phi basis? The basis is nothing but the AI xi hat. Actually, the characteristic vector of the ith subconstituent. And also the matrix representing adjacency matrix with respect to this standard basis is tridiagonal matrix. This entry is actually coincide with the intersection numbers of graph gamma. Now we said our Q-polynomial distance regular graph gamma has Q-Racah type whenever the primary Reynolds system phi has Q-Racah type. In other words, the corresponding parameter array, primary parameter array, has Q-Racah type. Actually, I showed earlier the Q-Racah type in terms of the parameters S star, R1, R2, etc. And we also saw that when we have a parameter arrays, then we can describe all intersection numbers in terms of all parameter arrays. So with this Q-Racah type, we can describe intersection numbers BICI as our parameters S star, R1, R2. This is all integers because we avoid all the degenerated situation. So throughout this lecture, we just assume that our graph has Q-Racah type. All right. Now we just discuss the concept of Delsarte cliques of gamma and the algebra T. Call the Q-Racah type graph gamma, and by a clique, this is just sub graph which is complete. So any two distinct vertex of this set is adjacent. So let's C denote a clique of graph gamma. Then it's well known that the size of C is bounded by the quantity we call the Hoffman bound or a Delsarte bound. We say our clique is Delsarte whenever the cardinality of this clique attains the upper bound. Just assume that our graph contains the Delsarte clique C. What is good for? So when we have the Delsarte clique C, let's construct the distance partition with respect to C. We have the last cell d-1 index because our covering radius is d-1. And now I'm going to define the quantity Ni of Z, where Z is a vertex in Ci. That is just the ith neighbor of Z in Delsarte clique C. So I just gave it some picture. The cardinality of this yellow portion. In fact, this number Ni is independent of the choice Z. Further, we can express this quantity Ni in terms of parameters R1, R2, S star, etc. Because we just assume that our graph is Q-Racah type. Now with this distance partition, C naught C1 through C d-1, and we choose a vertex Z from Ci, and let's think about these scalars, Ci tilde Z, Ai tilde Z, bi tilde z. That is nothing but just ci tilde z is just the neighbor of z in ci minus 1. And ai tilde is the neighbor of z in ci, and bi tilde is neighbor of z in ci plus 1. Then the following lemma shows that these numbers, this is actually the analog of the intersection numbers with respect to x. These numbers are independent of z. So here is the lemma. So actually ci tilde z is ni over ni minus 1 times ci, and bi tilde z is given by this quantity you see there. So it turns out that our the partition is equitable. So what does that mean? Whenever using two cells, say ci, cj, the neighbor of z in ci in cj is constant. It does not depend on the choice of vertex, only depends on the index. So here is the proof. So I'm going to prove the part 1. So to prove this, let's think about the set omega, the set of pairs of vertices, such that we choose y in C, that is the ith neighbor from Z. Recall our Z already chosen in CI, and also W is a neighbor of Z in CI minus 1. So we just count the pair of YW with respect to fixed vertex Z. Count this cardinality in two ways. First, by definition of Ni, we have Ni choices for Y, right? Because Y is in C, Y is the ith neighbor from Z. And for fixed, the vertex Y, we have exactly CI vertices in W, because this is, but we have a distance regular graph. So if you look at this triangle, then the number of W is nothing but exactly intersection number CI. So multiplying these two numbers, then we have the size of this omega NICI. Now we think of W first. So there are CI tilde Z choices for W by definition. And we fix W, then we exactly Ni minus 1 vertices Y by definition of Ni. So the size of omega is CI tilde Z Ni minus 1. So they equal to each other. So we obtain the formula for CI tilde Z. So similarly, we can find the formula for bi tilde of Z. So we just proved that our partition is equitable. So because we have this formula CI tilde bi tilde, they are expressed in terms of Ni intersection number CI, bi, and the C, the size of the delta clique. So everything can be parameterized in terms of the notation, the parameters R1, R2, S star. So this is the, let's say this guy, intersection numbers of gamma with respect to delta clique C. In 2005, Suzuki introduced the general version of Taylor algebra. So Taylor algebra of gamma with respect to the set of vertices. So we just take our set of vertices as delta clique for our purpose. Now we define the AI star tilde diagonal matrix, where yi entry is 1 if our vertex y is a member of CI, and we call this the dual primitive identitant of gamma with respect to delta clique C. And also we easily find these equations. So this element form a basis for commutative subalgebra M star tilde of met XC. And because Mi star tilde is diagonal matrix, also M star has a basis consisting of a diagonal matrix, so they commute each other. Do not follow, whenever you encounter the tilde notation, you just refer that expression related to delta clique C. And now we define the A star as this sum. the sum of A star of Y, the dual adjacency matrix of gamma with respect to Y, where Y is a member of C. Then this A star tilde is actually the sum of EI star tilde with some scalar, where this scalar is expressed as is there. Because, let me just prove this. To prove this equation, A star tilde is the sum of this expression. By definition, it suffices to check the ZZ entry of A star tilde is actually theta I star tilde. Prove this. Let's compute the ZZ entry of the original definition of A star tilde. That is just 1 over C times the sum of A star Y ZZ entry, where Y is the member of C. But Z is the vertex in Ci. So in Delsarte clique C, we have 2 parts. The vertex is distance from I distance from Z and I plus 1 distance from Z. So we can split this sum into 2 sum-ends. The first sum-end, the ZZ entry of A star Y is just theta I star. And such Y vertices, there are Ni choices by definition of Ni. Similarly, we have C minus Ni choices for such a vertex Y. And ZZ entry of A star Y is nothing but the I plus 1 star. So we just showed this equation, and we call this A star tilde the dual adjacency matrix with respect to Delsarte clique C. Now we define the subalgebra generated by M, and M is just a Bose-Nassau algebra and dual Bose-Nassau algebra with respect to C. And we call this T tilde topological algebra of gamma with respect to C. And this algebra is now same thing. So so finite-dimensional and non-commutative, and A star tilde generates T tilde, and this algebra is semi-simple. And now, for any subset Y in our vertex set X, we define Y hat, the sum of the lowercase y hat. So this is just a characteristic vector of Y. And now we think of MC hat. MC hat. Then this space has this problem. The vector Ci hat is just EI star tilde or one vector. And also, when we apply AI to each Ci hat, that is the combination of Ci minus 1 and Ci. Comment, we can show that MC hat is actually equal to M star tilde 1. So MC hat is the T tilde module. And also, MC hat has basis. So based on these properties, we can say that this MC hat is actually thin, irreducible T tilde module with endpoint 0, dual endpoint 0, and diameter d minus 1. We call this T module a primary. Now we have the primary T modules. Now let's think about the sequence of elements. This is just analogs of the level of the system on primary T module with respect to X. Then these elements act on MC hat as a level of the system. And what is the standard basis? That is the Ci hat. And with respect to this standard basis, we obtain the intersection numbers of phi tilde. Everything is very smooth, natural. And what is the parameter array corresponding to phi tilde? That is actually expressed as this. Actually, we can obtain this formula by comparing with the dual eigenvalue with respect to X and dual eigenvalue with respect to C. So it turns out that our level of the system, this has Q-Racah type. Now, we recall the topological algebra of gamma with respect to X and T tilde topological algebra of gamma with respect to C. So here I should remark that our vertex X is not arbitrary vertex in X. It should be a vertex in Delsarte clique C. Now we define the new algebra which contains T and T tilde. This is definition. So let bold T denote the subalgebra generated by T and T tilde. And this algebra T is finite dimensional, non-commutative, and this algebra is generated by 3 elements, A star tilde. And also this guy is semi-simple because it's closed under conjugate transpose. So likewise, ordinary T algebra, we define the bold T module. Bold T module, we mean the subspace W, such that BW is contained in W for all elements B. I call this just a generalized Taylor algebra, but it's not formal term. But for convenience, I just call it just a generalized Taylor algebra. All right, so next time, I think this is enough to review all the Taylor algebra theory. So likewise, theory with ordinary Taylor algebra, we will introduce the irreducible T module W, so-called the primary bold T module, and we will discuss its module structure in detail. So it's a natural starting point. Thank you.
So normally A star satisfies some relations. We have the same thing for the tilde. The people of all A star satisfy some Dolac-Brady relations or something like that. Yes. So couldn't say that. Oh yes, even T bold T case, and A star actually satisfies the TD relations, and A star tilde also satisfies the TD relations. And also one more relations, and A star tilde commutative. So, T algebra is a very powerful tool to study the Q polynomial distance regular graph. So I hope this algebra a little bigger, which means we may say more, right? So but the parameter is different between A star and A star tilde.
A and A star, same thing as the ordinary adjacency matrix and dual adjacency matrix with respect to X, and A star tilde is the dual
parameters entering in the defining relations. Do you know the parameters from the relation between A and A star tilde? Do you know the parameters entering in the relations? It's always the same. So.
To not go through, but the descendants belong to the same family in the possible cases. That's not going to work and help you figure out the parameter.
But A and A star tilde is not exactly the same thing as the relationship between A and A star. The TD relations, we have a different parameters. But yes. But I think the when we view a Q-Racah case, even the scalar different, everything can be parameterized in terms of R1, R2.
Oh yeah, so you're doing this generalizing Taylor algebras with respect to a Delsarte case.
Yes.
What about other large regular graphs? So what if you did like the biggest possible cocktail graph?
That's a great question. Actually, I think Hajime had studied about the Taylor algebra with respect to the set of vertices, not just only there's a clique.
So this theory generalizes to other.
Works nicely if you have a code. Some nice structure.
So that's the Delsarte case.
Right, there's any.
Oh, I see. You can do it with other.
Yeah, work out for the hand because the lane codes get beautiful so much.
Yeah, complete record. Yes.
So somewhere in the talk, you assume that the diameter is at least 3. And I see like d-2 popping up like several times, and like you have some I don't know, expressions for like bi tilde and stuff, I think it was. Does anything go horribly wrong with the diameter is 2? Like where would it break down?
Well, if diameter 2, then
Right. So our computation heavily relying on the Q. But if diameter D is strictly less than 3, just 2, then a Q has some algebraic problem. So a QTD, yeah.
So like it breaks down somewhere.
So the Q is defined in the first place by taking, for example, the sequence of eigenvalues depending on theta to D, and that satisfies the Friedman recurrence. The parameters of the recurrence, you get the Q. But if the D is only 2, the sequence is so short that there are multiple, you can't really uniquely define the parameters of the Friedman recurrence.
In general, strong irregular graph is the different topic.